Okay, good morning. Welcome to the class. So from today on, we're going to have a look at the last chapter of this lesson, which is chapter 6, lines and planes. So today, let's have a look at the first lesson in this chapter, which is about the equations of lines in 2 space and 3 space. Okay, first of all, let's have a look at today's learning goals. After this lesson, you are expected to be able to understand the concept of vector equation, parametric equation, and normal vectors of a line in 2 space and 3 space. Then express the equation of a line using scalar equation, slope-intercept equation, vector equation, and parametric equation interchangeably in 2 space. Also express the equation of a line using vector equation and parametric equation interchangeably in 3 space. Okay, so we'll have a look at the concepts one by one. First of all, let's have a look at the vector equation of a line in 2 space. Okay, remember that we have learned in our previous lesson. In 2 space, a line can be defined by an equation in a standard form, right? Which is ax plus by plus c equals 0. This type of equation is also called the scalar equation of a line, or in the slope-intercept form, as long as the slope exists, right? Slope-intercept form is y equals mx plus b, where m is the slope of this line, and b is a y-intercept. So as we have learned vectors in previous chapter, note that vectors can also be used to define a line in 2 space. So let's consider the line defined by negative x plus 2y minus 10 equals 0. A direction vector parallel to this line is m, whose position vector is 2, 1, right? Can you see that? Which is shown here on the graph on top right. So note here, this position vector m is parallel to this line. So we can use this to denote the direction vector of this line, which is parallel to the line. A position vector that has its tip on the line is r naught, which is 2, 6. Which is also shown here on the graph on top right. So note that this point here is a point on this line. So the point has a position vector r naught. Another position vector such as r, which is 6, 8, can be drawn to form a closed triangle. The third side of the triangle is the vector s, which is here. This is a vector. There's another vector, and this is another vector, right? The closed triangle can be represented by the vector sum. Note that we have learned the triangle rules, right? Vector r equals r naught, which is here, plus s. Can you see that? Since vector s is parallel to vector m, it is a scalar multiple of m. So we know vector s can be represented by t times vector m, right? Where t belongs to the real number set. We can substitute s equals tm into r equals r naught plus vector s to get this relationship. Vector r equals vector r naught plus t times vector m, where t belongs to the real number set. So this is called the vector equation of a line in two space. In a vector equation, the variable t is a parameter. By changing the value of t, the vector r can have its tip at any specific point on the line. Okay, I'll give you some time to have a look at the concept here. Any questions, just let me know, okay? Okay, do you have any questions? All right, if no questions, let's continue. So note that we have learned that this is a vector equation of a line in two space, right? In a vector equation, the variable t is the parameter. By changing the value of t, the vector r can have its tip at any specific point on the line. And also we can substitute r using its position vector xy, and r naught using its position vector x naught, y naught. And m with this position vector m1 and m2 to write an alternative form of the vector equation like this. So r equals r naught plus t times m is equivalent to this form of equation. Xy equals x naught, y naught plus t times m1, m2. So basically, we substitute these three vectors using their position vectors, coordinates of the position vectors, right? So both of these two equations are the vector equations of a line in two space, and usually we use the second equation more often, where t is a real number and vector r, whose position vector is xy, is the position vector to any unknown point on the line. And vector r naught, whose position vector is x naught, y naught, is a position vector to any known point, no point on the line. And m, whose position vector is m1, m2, is a direction vector parallel to the line. Okay, again, I'll give you some time to have a look at this concept here. Make sure you understand the concept of vector equation of a given line, okay? Okay, do you have any questions? No questions? Let's have a look at the example, okay? So since we have learned the concept of vector equation of a line into space, let's consider an example practice. Can you write a vector equation for the line through the point A, whose coordinates is 1, 4, and point B, whose coordinates is are 3, 1, and determine if the point 2, 3 is on the line using vector equation of this line. Okay, I'll give you 5 minutes to have a look at this example question.
老师，我是嘉禾，我那个刚才电脑重启，然后就我们会议自动退出，现在在那个等候室里面，让我进一下会议。
Okay, have you finished? Then let's have a look at the solution together. Okay, first of all, we need to determine the vector from point A to point B to find the direction vector, right? Well, you can also find the vector from point B to point A. Does not matter as long as it's the direction vector of this line. So the direction of the vector of this line, sorry, the direction vector of this line M is given by OB minus OA, which is 2, -3. So according to the vector equation of this line, xy equals x naught y naught, which is a given point on this line, right? And the t times a direction vector of this line. So now here we have known a direction vector of this line, which is 2, -3. And we also know that a point on this line, the position vector of this point is 3, 1, right? So we know R naught and direction vector M. So a vector equation of this line can be written as xy equals 3, 1 plus t times 2, -3. Note that 3, 1 is a known position vector of the point on this line, and 2, -3 is a direction vector of this line. T is a real number, right? Any questions? Okay, so let's have a look at question B. If the point 2, 3 is on this line, then the position vector 2, 3 has this tip on this line, right? So there exists a single value of t that makes the equation true. So we can let xy equals 3, 1 plus t times 2, -3. That becomes 2, 3 equals 3, 1 plus t times 2 times -3. So we can equate the x coordinates as follows. 2 equals 3 plus 2t, which gives us t equals -1/2. And also equate the y coordinates. 3 equals 1 minus 3t, which gives us t equals 2/3. Since the t values are not equal, therefore there is no solution of t such that the x coordinates are equal and the y coordinates are equal, right? There is simply no solution for this. So the point 2, 3 does not lie on the line. Okay, any questions? So this is how we can solve a problem using the vector equation of a line. Okay, I'll give you some time to have a look at the solution here. Any questions, just let me know, okay? All right, if you don't have any questions, let's have a look at another concept, which is called the parametric equation of a line, which is another type of the equation of a line in two space. Remember that we have just learned the vector equation of a line in two space, which is given by r equals r naught plus t times vector m, right? Or xy equals x naught, y naught plus t times m1, m2. The vector equation of a line can be separated in two parts, one for each variable. These are called the parametric equations of a line. Because the result is governed by the parameter t, where t belongs to the real number set, the vector equation r equals r naught plus t times m can be written as xy equals x naught, y naught plus t times vector m1, m2. The parametric equations of a line in two space are represented in this way. First of all, x equals x naught plus t times m1. And then y equals y naught plus t times m2, where t belongs to the real number set. Well, basically, it's the same thing with the vector equation, right? If you have the vector equation, then you can write the parametric equation of this line. Also, if you know the parametric equations of a line, then you can also write its vector equation. Any questions? Okay, I'll give you 2 minutes to have a look at the concept of parametric equation of a line in two space. All right, if you don't have any question, let's have a look at an example. Check your understanding of the parametric equations of line in two space. So consider line L1, whose parametric equations are given by x equals 3 plus 2t and y equals -5 plus 4t, where t belongs to the real number set. Then find the coordinates of 2 points on the line. Write a vector equation of this line. Write the scalar equation of this line. And last, determine if the line L1 is parallel to the line L2, whose parametric equations are given by x equals 1 plus 3t, y equals 8 plus 12t. Okay, I'll give you 5 minutes to have a look at the example yourself. And after that, we'll have a look at the solution together, okay? All right, have you finished? Any ideas? Okay, let's have a look at the solution together. So first, find the coordinates of 2 points on the line. If you know the parametric equations of this line, so we can let t be any real numbers to get the point on the line, right? For example, the easiest way to let t equal 0 or 1 or -1, right? Okay, so following this logic, for example, we can let t equal 0. This gives a point P1, whose coordinates are 3, -5. So that's a point on this line, right? Then to find another point, choose any value of t. So for example, we can let t equals 1, which is much easier to calculate the coordinates, right? And then x equals 3 plus 2 times 1, which is 5. Y equals -5 plus 4 times 1, which gives us -1. So the coordinates of the 2 points on the line are 5, -1, and 3, -5. That's the 2 points on the line. Of course, you might have different answers by letting t equals some other values, right? Any questions for question A? Okay, so for question B, from the parametric equations, we can choose R0 equals 3, -5, right? And the direction vector M is 2, 4. So a possible vector equation is given by xy, the vector f xy equals vector 3, -5, plus t times the vector 2, 4. And note that parameter t is usually placed before the direction vector to avoid ambiguity. Also, you can verify your result by converting the vector equation to the parametric equations. So from this vector equation, you can see that x equals 3 plus 2t, right? And y equals -5 plus 4t, which is exactly the parametric equation here. Okay, any questions? Okay, if no questions, next let's have a look at question C, which is a scalar equation of this line. So for the scalar equation of this line, we can isolate t in both of the parametric equations. Note that x equals 3 plus 2t, right? Therefore, we have t equals x minus 3 over 2. On the other hand, y equals -5 plus 4t, which gives us t equals y plus 5 over 4. So note that in the scalar equation of the line, we don't have the parameter t, right? So according to these equations, we have x minus 3 over 2 equals y plus 5 equals 4. That's the connection between x and y, the two coordinates. And we can simplify this to 4x minus 12 equals 2y plus 10. Then we know the scalar equation of this line is given by 2x minus y minus 11 equals 0. Okay, any questions? Okay, if no questions, let's have a look at question D. If two lines L1 and L2 are parallel, we know that their direction vectors must be parallel, right? Which means the direction vectors of parallel lines are scalar multiples of one another. So let's check if this is the case in question D. For line L1, we know the direction vector M1 is 2, 4, right? And for line L2, the direction vector is here. Well, you can write this to vector xy equals a point. Well, the position of vector of a point 1, 8 plus t times 3, 12. That's the vector form of the line L2, right? So this vector here is called the direction vector of line L2. So the direction vector for L2 is vector M2, which is 3, 12, right? If these lines are parallel, we need to have 2, 4 equals k times 3, 12. Well, we can try to solve this system to see if there is any solution. So first of all, 2 equals 3k, right? That gives us k equals 2/3. Next, we must have 4 equals 12k, which gives us k equals 1/3. So as you can see here, there does not exist a single value of k such that the x coordinate equals of y coordinate. Therefore, the required k value does not exist. There is simply no solution to this system. So we know line L1 and line L2 are not parallel. Okay, any questions? I'll give you 2 minutes to have a look at the solutions again. Any questions, just let me know, okay? Okay, any questions? Okay, if no questions, you can take a 10 minutes break and please return before 10:40 and next we'll have a look at another example. Okay, you can take 10 minutes break now. Okay, welcome back. So now let's consider another example. Consider the line with a scalar equation, 4x plus 5y plus 20 equals 0. First of all, graph this line and then determine a position vector that is perpendicular to this line. How does this position vector from part B compare to the scalar equation? Next, write a vector equation of this line. Okay, I'll give you 5 minutes to have a look at the example here. Okay, have you finished? Now let's have a look at the solution together. So first of all, it's easy. It's very easy to sketch the graph of this line, right? For example, we can let y equals 0, and then we know the x-intercept is -5. And then we can let x be 0, then y-intercept is -4. Then we can connect these 2 points to find the sketch of this line in the 2D Cartesian plane, right? Okay, for question B, find the direction vector of this line. Well, first of all, we can find the direction vector of this line using OB minus OA, vector OB minus vector OA, right? And then put all the coordinates in. So that gives us the direction vector of this line is 5, -4. Then to find the vector D, xy, that is perpendicular to M, we need to find a vector whose dot product with the direction vector is 0, right? Remember that 2 vectors are perpendicular is equivalent to the dot product between these 2 vectors is 0, right? So that basically gives us 5x minus 4y equals 0. Therefore, we know y equals 5/4x. So we can choose any value for x. By observation, we know x equals 4 is a convenient choice, right? So a possible vector that is perpendicular to the direction vector m could be 4, 5. So d equals 4, 5 is perpendicular to the line. If you sketch the vector d, that is shown on the graph on the right side here. The vector highlighted in red. This is the vector d. Also note here, you should use the square parentheses here to indicate the position vector for vector d. Okay, next, the components of vector d correspond to the coefficients of x and y in the scalar equation, right? Okay, note that the x component is 4, y component is 5, right? And also, you can see that the scalar equation of this line is here. The coefficient of x is 4, and coefficient of y is 5. So 4, 5 is a vector that is perpendicular to this line. That's connection between the components of the vector perpendicular to this line and the coefficients of x and y. Okay, last question. To write a vector equation, we need a position vector and a direction vector. We know a vector equation of this line is given by xy equals -5, 0. That's a position vector of the point on this line, right? Here. The coordinates of this line is -5, 0. We can use the direction vector of this line here, and then plus t times 5, -4. So 5, -4 here is the direction vector of this line, and t belongs to the real number set. Okay, these are the solutions to the questions here. Do you have any questions? Okay, so this example shows us how to find a vector that is perpendicular to this line, right? So next, let's have a look at the concept here. Normal vector to a line in two space. Well, a normal vector to a line L is a vector n that is perpendicular to this line. If the scalar equation of L is given by ax plus by plus c equals 0, then the perpendicular, then the normal vector is given by AB. The vector AB here is the position vector for the normal vector to this line. Okay, so you can try to prove this using the Cartesian vector after this class. I'm not going to show you how we can prove this. Okay, so for example, given the equation of a line L, whose equation is 4x plus 5y plus 20 is 0, then a normal vector of L can be given by vector n is 4, 5. The two components 4, 5 corresponds to the two coefficients of x and y. Okay, have a look at this concept, and any questions, just let me know, okay? Okay, if you don't have any questions, then let's make a summary for the equations of a line in two space. So in two space, a line can be defined by an equation in slope-intercept form, a vector equation, a parametric equation, or a scalar equation, as shown here in this table. The points x, y that are the solutions of these equations form a line in two space. So in slope-intercept form, we have the form y equals mx plus b. M is the slope of this line, b is the y-intercept. In the vector form, we have the vector r, which is the position vector of any point on this line, equals r naught plus p times vector m, where p belongs to the real number set, which is equivalent to vector xy equals x naught y naught plus t times m1 m2, where the vector r, whose position vector is xy, is a position vector to any point on that line. And the vector r naught, whose coordinates are x naught, y naught, is a position vector to a known point on this line. And the vector m, whose position whose two components are m1, m2, is a direction vector for this line. And last, we have the scalar form of the equation of a line, which is ax plus by plus c equals 0. And if you have this form of equation for this line, we automatically know that a vector n whose components are a and b, which are the coefficients for x and y, is a normal vector to this line. Okay, do you have any questions? So that's the types of equations of line in two space. Next, let's discuss the equations of a line in three space. So in three space, the slope of a line is not defined. So a line in three space must be defined in other ways. A line in three space can also be defined by a vector equation or by a parametric equations. It cannot, however, be defined by a scalar equation. In three space, we will see that a scalar equation defines a plane in our next lesson. A plane is a two-dimensional flat surface that extends indefinitely far in all directions. So we'll talk about the equations of a plane in our next lesson. So next, let's have a look at the equations of a line in three space. Okay, remember that we can define a line using a vector equation and parametric equations in two space, right? Similarly, we can also define a line in three space using a vector equation or using parametric equations. So first, let's have a look at the concept of vector and parametric equations of a line in three space, which is very similar to the cases in two-dimensional space. The line passing through the point P naught with position vector R naught, whose components are x naught, y naught, 0 naught, and having direction vector M, whose components are M1, M2, M3, has vector equation like this. R equals R naught plus T times the vector M, where T belongs to the real number set. Or you can also write it in the form of vector x, y, z equals vector x naught, y naught, z naught plus t times vector m1, m2, m3, where the vector x, y, z is the position vector of any point on that line. And the vector x0, x naught, y naught, z naught is the position vector of any known point on that line. And the vector m1, m2, m3 is the direction vector for that line. And correspondingly, the parametric equations of a line in three space are given in this way. X equals x naught plus t times m1. Component y equals y naught plus t times m2, and component z is given by 0 naught plus t times m3, where t belongs to the real number set. So basically, as in two space, a direction vector and a position vector to a known point on the line are needed to define a line in three space. Okay, I'll give you 2 minutes to have a look at the concepts here. And after that, we'll have a look at an example. Okay, now let's have a look at a example to check your understanding of the vector and parametric equations of line in 3 space. Okay, so a line passes through points A, whose coordinate is 2, -1, and 5, and point B, whose coordinates are 3, 6, and -4. Question A, write a vector equation of this line. Question B, write parametric equations for the line. And then determine if the point C, whose coordinates are 0, -5, 9, lies on the line. Okay, I'll give you 5 minutes to have a look at this question by yourself, and then we'll have a look at the solution together. Okay, have you finished? Okay, any thoughts? Okay, note that the vector equation of a line requires a position vector of a known point on the line, right? And the direction vector of this line. So if you know 2 points on the line, then the direction vector can be easily found by using either vector AB or vector BA, right? And also, if you know a point on that line, you could use either A or B as the position vector for the given point on that line. Okay, so following this logic, first of all, we can find a direction vector M, which is vector OB minus vector OA, which is given by 1, 7, -9. So 1, 7, -9 is the direction vector for that line. Therefore, a vector equation of that line is given by vector x, y, z equals the position vector of a given point of that line. So for example, we can use point A, right? 2, -1, 5 plus t times the direction vector of that line, which is 1, 7, -9. And t belongs to the real number set. And the question B, therefore, the corresponding parametric equations are x equals 2 plus t, y equals -1 plus 7t, and z equals 5 minus 9t. Okay, next, to check if a point is on that line or not, we can substitute the coordinates of C, which are 0, -15, 9, into the parametric equations and solve for t. If you can find a solution for t that satisfies both x, y, and z, then that point must lie on that line, right? Otherwise, that point is not on that line. So in this case, we have 0 equals 2 plus t, which gives us t equals -2, and -15 equals -1 plus 7t, which also gives us t equals -2. But for the z component, we have 9 equals 5 minus 9t, which gives us -4/9. That means there is no single value of t such that all of the x, y, and z component can be fulfilled. That means there is no solution. So the t values are not equal, right? This tells us the point does not lie on that line. Okay, have a look at this question here. Do you have any questions? All right, do you have any questions? If not, let's have a look at the concept of the normal vector to a line in three-dimensional space. Okay, a line in two space has an infinite number of normal vectors that are all parallel to one another, right? A line in three space also has an infinite number of normal vectors, but in this case, they are not necessarily parallel to one another. For example, in this diagram shown here below, we can draw two normal vectors to the line highlighted in blue, right? Apparently, these two vectors, n1 and n2, are not necessarily parallel to each other in three-dimensional space. Okay, any questions? Okay, so this is what you should be careful with, okay? And now let's make a summary of the equations of line in three space. So in three space, a line can be defined by a vector equation or by parametric equations. So note here, in this case, the line cannot be expressed using a scalar or a slope-intercept form of equations. First of all, the vector form of the equations of a line in three space is given by vector r equals vector r naught plus t times vector m, where t belongs to the real number set. Or you can also write it in this way. Vector x, y, z equals vector x naught, y naught, 0 naught, plus a real number t times vector m1, m2, m3. So note that r equals x, y, z is a position vector to any point on the line. And vector r naught, whose components are x0, y0, and z0, is a position vector to a known point on the line. And vector m, whose components are m1, m2, m3, is a direction vector for the line. And correspondingly, the parametric equations for this line is given by x equals x naught plus t times m1, y equals y naught plus t times m2, and z equals z naught plus t times m3, where t belongs to the real number set. Okay, so have a look at these two types of equations of a line in three-dimensional space. Do you have any questions here? Okay, so that's the end of today's lesson. So today we have talked about how to express lines in two-dimensional space or three-dimensional space, right? In other words, the equations of a line in two space or three space. So after this lesson, now you should be able to understand the concepts of vector equation, parametric equations, and normal vector of a line in two space and three space. Also express the equation of a line using scalar equation, slope-intercept equation, vector equation, and parametric equations interchangeably in two space. And then express the equation of a line using vector equation and parametric equations interchangeably in three space. Okay, so if you don't have any questions, remember to complete our homework and submit them onto Google Classroom before the deadline, okay?